right, so we're starting a new unit, work and power. This is probably one of the most important units that we get to. Work and power, because a lot of what we talk about is work. When are we doing work? Work has to do with energy, and energy creates power. So, our focus question for today is, when does a force do work? And how to calculate the work done on an object. So how do we do this? Well, first thing we need to define is, what is work? All right, so the physics definition is force times distance in the direction of the force. Okay, so what does that tell you? That gives us a definition. When force and motion are in the same direction, that means that work is equal to FD. Now, when we talk about in the direction of the force, we are talking about actually work being defined as a dot product, F dot D, which means that when work and motion are not in the same direction, in other words, what happens if this is for force in the same direction, this would be force parallel. And sometimes you'll see it on your sheet as force parallel. When force and motion are not in the same direction, in other words, when we've got something here, we've got a block, and the force is at an angle right here, some angle theta, then we know this component of the force right here, this part that is actually in the direction of the motion would be F cosine theta. So what we know, if the direction of the force is D going this way, so our actual definition of work becomes FD cosine theta, which, if you remember, is a dot product. And in other words, we can only do work when the force is in the same direction, or the component, let me say this differently, the component of the force that does the work is in the same direction as the motion of the object. So, and that cosine tells us that, because if they're going in the same direction, that angle, if they're parallel, that angle is 0. So, think about it. Cosine of 0 degrees is 1. Cosine of 180 degrees, which would also be in the opposite direction, would be -1. So it's still work, but it's negative work because it's in the opposite direction of the direction it's moving. If it's perpendicular, then 90 degrees, and cosine of 90 degrees is 0. In other words, you cannot do work if the force is at a 90-degree angle to the object, the direction the object is moving. So if I have something that is moving across the floor in this direction, but the force is going this way this time, and that is 90 degrees, then it does no work on that object. In other words, it's not going to help it or hurt it. It's just up or down, and it's going side to side. So we've got F dot D. Okay, so when work is done, it's independent of the object. Okay, it is a conservative force. Independent of path is what tells us it's a conservative force. Now, what are the units of work? Work is joules. And we use J for that, joules. All right? And this will get confusing next time. This is joules, this J, because when we cover momentum, impulse also uses the letter J, but it's in a different context there. So, let's look at some examples and see if we can figure out what work is done in the following cases. And it says justify it. Weightlifter holds a 300-pound weight over his head. Well, if he's holding a 300-pound weight over his head, if it's not moving, in other words, D is equal to 0, then work, which is FD, would also be equal to 0. In other words, there's no work, no displacement, equals no work. Now, I bet you would argue that. You'd say it's hard work holding a 300-pound weight up over your head. Well, that's muscles internally are doing what do your muscles do? They contract and expand. Well, that's motion, so that's displacement of your muscles. But technically speaking, we've defined the system as the entire guy, and he's just holding it there. The weight itself isn't moving. So in that particular context, no work is being done. Okay? Hockey puck moves at a constant speed on a frictionless surface. Well, constant speed means that acceleration is 0, which means that the force is 0, which means what? Work, which is FD, would also be 0. Okay? So if there's no change in speed, then you don't need any force. Remember, force causes a change in inertia. Well, that's acceleration. That's due to acceleration. No acceleration means no work done. Now it says a crate is pushed across the ground at a constant speed. This one is an interesting one. We've got a constant speed, which means we have an acceleration of 0, but this is not necessarily frictionless. So this is kind of a yes and no guy. We would say that the net force would be equal to 0, right? Here, because this isn't just force equals 0. This is net force is actually what we're talking about. So there probably is work being done. The push is causing a positive force, but the ground, there's friction, which is a negative force. So they're equaling out. So what you've got is a sum of forces, a net force, which is 0. So therefore there is no net work being done, which is 0. Now, work can be positive or negative. Work is positive if what? The force is in the direction of the displacement. Okay? Work is negative if the force is in the opposite direction of the displacement. And work is 0, or no work is done if the force is perpendicular to the direction of the displacement. Okay? So now, skier skis down a slope. It says draw a free body diagram of the skier's motion and identify the force that does positive work, force that does negative work, and a force that does no work. Okay, so what's the free body diagram going to look like here? Free body diagram for this guy going down. Yeah, free body diagrams are not going away. So what do we know? We have the force due to gravity or weight. We have a normal force here. And we have what? Frictional force, don't we? Going this way. Okay, well, the skier is going which direction? His direction, or its acceleration, right, is going down the slope there. So immediately we can see that positive work is going to be, we're going to break this guy down into his components right here. And this, of course, is our theta. So this is going to be FW cosine theta. And this, of course, is going to be F sub W sine theta. So positive work would be the one in the same direction as the acceleration, which would be our F sub W sine theta. That is the force that does positive work. Okay? Now, negative work would be whatever's in the direction opposite the motion, which would be force of friction. And also, no, that would be it. And then C, force that does no work would be the perpendicular forces, which would be the normal force and the component of gravity that is perpendicular, which would be F sub W cosine theta. Okay? So those would be the guys that would be negative work, positive work, and no work. All right, so now, in order to write a physics problem, a physics teacher makes a stick figure, love me a stick figure, push a refrigerator across a rough floor as shown. The force of the push is 300 newtons, so we've got a force going in the same direction. So there's work being done there. The refrigerator is a mass of 120 kilograms. It's a big fridge. Coefficient of friction is 0.2, so we know we have friction going the other direction. So we have F push that way, we have F friction going this way against. So calculate the work done by the stick figure. So A, work done by the stick figure is going to be equal to F sub push times the distance, won't it? Okay, well that's going to be 300 newtons times a distance of 2 meters, which is going to be 600 Newton meters. And since we said Newton meters, just so you know, 1 Newton meter is equal to 1 joule. This is going to be 600 joules. Positive work done. Now part B, work done by friction. So this is work push. Work done by friction is going to be the force of friction times the distance. That is going to be in the opposite direction, and that'll come out in the sign. This is a negative force, so negative force of friction is going to be mu times the normal force times d. So that's going to be negative mu times, in this case, the normal force would be mg times d. So we have negative 0.2 times 120 times, not 1200. Oops, got crazy on my zeros there. 120 times gravity, which would be about 10, times the distance, which is 2. So this is going to end up being negative, 480 Newton meters, which is negative 480 joules. And then C, is it gaining or losing energy? Well, that's going to be the net force, or net work, excuse me. Net work is going to be the positive with the push plus the negative gravity working against it, which still leaves us with a positive 120 joules. So it is a positive overall work. So it is a gain in energy. Okay? So now, example D. Force of 70 newtons is applied to a 20 kilogram force. 20 kilogram object. Object accelerates on a horizontal frictionless surface. So we know it's frictionless, it's horizontal. If it starts from rest, this is, the V initial is 0. How much work is done in the first 5 seconds? Ooh, this one's interesting. So we know work is equal to force times the distance. We don't know how far though. We got to find distance. Well, how are we going to find distance? We've got an initial velocity, we've got a time, and we need to know what the acceleration is, don't we? Or the distance. What is the acceleration going to be? We don't know the acceleration. What do we know? Acceleration is equal to force divided by mass, right? Sum of the forces. Well, the only force we have is 70 divided by the mass of 20, which leaves us with 3.5 meters per second. So that's how it's accelerating. So now we can use kinematics, can't we? The distance that it goes is going to be what? V initial t plus 1/2 at squared. Well, V initial is 0, so it's just 1/2 acceleration, which is 3.5 times the time squared. 5 squared, 25. Half of that, we end up with 43.75 meters. So we're using a combination of kinematics. We also use Newton's second law to find the acceleration to plug into the kinematics. So now we can take that force, 70 times the distance of 43.75 meters. And we end up with 3,063 Newton meters, which is 3,063 joules of work done in the first 5 seconds. Now, work using a force distance graph. Well, if you think about it, work is equal to force times distance. Well, if we have force on one axis and distance on the other axis, force times distance is going to be the area under the curve. And look what it says. Work done on a force distance graph is area under the curve. So that's what we're going to actually look at. So if we want to find the work done on an object. Now, why do we even care about this? Well, what if the force is not a constant force? As you can see here, the force is not constant. We've got a changing or variable force that makes it easy to do it this way. So this is from work done on the object from 0 to 0.2 meters. Area under the curve, this is a triangle. So that is going to be 1/2 base, which is your distance, which is 0.2, times your height, which is your force, which is 15. If we take and look at this, we get 1.5 joules or Newton meters, right? Now, just as a preview, if any of you decide to take it next year or take calculus, in calculus work, which is the area under the curve, is an integral. It's defined as the integral of f dx. So now, let's look at how do we calculate power, because we've talked about work now, and we've talked about work kind of as energy, because if you remember, energy is joules also. Work, the physics definition, is the rate at which work happens. In other words, the rate at which work is done, in other words, power is energy transfer. Work over time, isn't it? Power is work over time. So work over time equals power. And that would be what? W over T. W is FD over T. And we're going to look at this. Now, this is often the first description you get, but FD over T, you could do F d over t, because an alternative definition, d over t, is velocity. Distance over time is velocity. So FD is the alternative to power. So we have power, which is equal to W over T, which is equal to FV. Units of power, well, work is joules, power or time is seconds, so 1 joule per second, which is actually equal to 1 watt. Okay, it's watts, which is W. So units of power is watts or W. Okay, watts for power, not W for work. All right, so an example. Mario climbs the top of a 20-meter tall flagpole in 10 seconds. Next level, he climbs a similar 20-meter tall flagpole in 5 seconds. In both cases, Mario does the same amount of work. In which case is there more power developed? In other words, we've got time going down, power going up. So it takes less time in the second case to do the same amount of work. Or if you think about it as power equals FV, that force is being applied faster in the second case. So he's using more power. Curtain needs to be raised at a constant speed in 5 seconds. What's the power required to raise the curtain? Well, power equals FD over T. F is mg, right? So mgd over T. So what do we know? We know the mass is 200, gravity is 10, distance is 7.5 meters, divided by the time, which is 5. So we can manipulate this formula to use what we're given. If we do all of this, we end up with 3,000 joules per second, which is the same as saying 3,000 watts of power is needed to raise that curtain. Yep, sure did. All right. Let's look at our, let's make sure. Did I get that entire? All right, so here we go. Car of mass M drives at a constant speed. V up an incline that makes an angle theta with the horizontal. Oh, one thing I did want to mention is efficiency on that last one. Efficiency, by the way, efficiency is E, script E. That would be the power used divided by the power of provided. In other words, if we were using a motor, it would be the power of the motor versus how much power was used. Let's say we had a 3,500 kilowatt motor. Looking at that last example, then our efficiency would be the 3,000 watts used divided by the 3,500 watts of the motor that was available. And we would end up with 0.86, which would be an 86% efficiency. Okay? Car of mass M drives at a constant speed V up an incline, making an angle. All right, so let's start with your free body diagram. Free body diagram, if we're going up an incline, what do we have? We have friction. So if this guy is going up an incline, we have friction going down the incline. We have the force of gravity or force of weight this way. We've got the normal force going this way, and then we have the force of an engine providing a force to go up the incline. So now I'm going to break this guy down into his components, at least this one. So we've got a chunk this way and a chunk this way. This, of course, is FW cosine theta. This chunk is going to be F sub W sine theta. And we're going to use this to come up with our work done with friction. So A, work done due to friction, is going to be the force of friction times the distance. Well, the force of friction is going to be mu times the normal force times the distance. Well, what is the normal force here? Normal force, if you look at our diagram, is F sub W cosine theta. So this is going to be mu F sub W cosine theta times the distance, and F sub W, of course, is going to be mg. So mu mg d cosine theta. So that is the work done. It, of course, is done opposite the motion, so it is negative. B, what's the power output by the engine? Well, the power output by the engine would be the force of the engine times the velocity, v, okay? So the force provided by the engine is going to be the sum of the forces. If you think about it that way, it's going to be the net force, right? If this thing is going at a constant what? Constant speed means there's no acceleration. So the net force is equal to 0, which means that the force of the engine has to be equal to the force of friction, which we know. All right, so the power put out by the engine is going to be mu mg d cosine theta times the velocity v. Okay? And that would be the power output by the engine. So we're still using, I hope you notice how I figured this out, the F of the engine. I'm still looking at Newton's second law of force, and Newton is not going away, guys. You've got to be able to do these free body diagrams. You've got to be able to look at those to find and manipulate. Now, your purple sheet is only going to have power being equal to work over time or force times velocity. It is not going to have these other little chunks. You're going to have to be able to manipulate the free body diagrams to come up with and read them to understand what's going on, that this guy is equal to this guy and that this is equal to this. And I use both of those relationships from the free body diagram to figure out the power and the work. All right, so you need to be thinking about, what do I know? What do I not know? How do I figure this out? How do I use Newton's law? And if you think about it, in this lesson, we've used Newton's law, we've used kinematics, along with some new definitions. So I will talk to you in class. We'll wrap up, and then you'll be doing work.